Good morning, students. Today we are going to start 7th unit of your crash course, Behavior of Gas, Behavior of Gas, Perfect Gas and Kinetic Theory of Gases. It is unit number 7. Unit 7 of your crash course program. From your crash course program, it is behavior of perfect gas and kinetic theory of gases, KTG, a very important unit. Very laws are common to chemistry also. So what is an ideal gas? Remember what we are saying. We are saying for ideal gas, it means we are assuming that size of gas molecules is 0, nearly 0, and there is no attraction between gas molecules. So assuming this, many scientists give many laws, and it is ideal gas equation. PV is equals to mu RT. PV is equals to mu RT, mu number of moles, R universal gas constant, T temperature, P pressure, V volume. If we are putting temperature constant, then it will become PV is equals to constant. It means it is known as Boyle's law. If we are putting P constant, it is V proportional to T. In this we assume T constant. If we are assuming P constant, then V proportional to T. It is known as Charles' law. Assuming P constant. If we are assuming V constant, P proportional to T, it is known as Reynolds or Gay-Lussac's law, or Gay-Lussac law. We are assuming V constant. One Dalton's law is also there. Dalton's law. Means at same pressure, same temperature, same volume of all gases. Contains same number of molecules, same number of molecules. After that, one law is related to pressure. If you have a mixture of gases, it is known as, it is not Dalton's law, at same pressure, same volume, it is Avogadro's law. It is Avogadro's law. Avogadro's law. That same pressure, it all laws from your chemistry syllabus. Dalton's law is related to pressure. If you have a mixture of gases, Dalton's law is related to partial pressure. Means if in your mixture there are so many gases, so total pressure should be equal to sum of individual pressures. This type. Mainly from physics purpose, kinetic theory is important. So we will go in detail with kinetic theory of gases. But you know that real gases, we cannot assume molecule size 0, we cannot assume they are not attracting each other. So after considering these facts, van der Waals gave correction. What was the correction of van der Waals? Instead of P, we should write P plus A upon V square. Instead of B, we should write V minus B. It should be equal to RT. It was van der Waals correction. It is van der Waals correction. A and B are van der Waals gas constant. For neat purpose, these three formulas are very, very important. One is critical temperature, 8A upon 27 RB, 8A upon 27 RB, and critical pressure, A upon 27 B square, and critical volume, 3B. What are these? You know that if you are increasing the pressure beyond a limit, you can liquefy the gas. But temperature should not be more than a particular value. That is this TC. TC means critical temperature. PC means critical pressure. VC means critical volume. So critical temperature means the maximum temperature up to which you can liquefy gas by pressure only. Otherwise, if you are reducing the temperature, you can liquefy gas. But with pressure, if you want to liquefy gas, it should not be greater than this temperature. And if gas is at TC, means critical temperature, what pressure you required, that is known as critical pressure. Critical pressure means pressure at critical temperature needed to liquefy the gas. At this pressure and this temperature, volume is known as critical volume. So remember these three formulas. Sometimes they are asking two in same paper. So be aware that these are very important results. Now we are going to discuss what is the kinetic theory of gases, means pressures formula. If you make your concept clear for this, whole chapter is only based on this. So what we are assuming, we are taking 1 cuboid 1, we are taking 1 cube of length L, and in this we are taking one ideal gas. So there are see, it is a cube of length L. Suppose it is origin. Take this line x-axis, this line y-axis, and this line z-axis. If I am naming the cube A, B, C, D, I am assuming origin at A. E, this point is E, F, G, H. We know the fact that gas is putting equal pressure on all sides. Means what pressure is it? It is putting on the walls which are along x-axis. Same pressure it will put along the walls on y-axis, same along the walls z-axis, and it should be equal to pressure of gas. Suppose in this container there are n molecules of gases. This gas contains n molecules. I am considering one molecule. It was moving with velocity u1 in this direction. Its mass was m. So I am considering only this molecule which is moving towards any random direction with velocity u1. I resolved its velocity in 3 components. In x component ux1, its y component I am taking uy1, and in the direction of z-axis its component assume uz1. So it means you can consider, you can imagine that your molecule is moving in the direction of x-axis with velocity ux1, or it is every time we are writing x1, x2, or we will do this, take this molecules velocity in the direction of x-axis u1, v1 and w1. So its velocity now I am taking c1, easy to write, x component u1, y component I am considering v1, and z component I am considering w1. By the law of vectors we know that c1 square is equals to u1 square plus v1 square plus w1 square. By law of vector addition we know this, कि since these 3 components are mutually perpendicular, so resultant should be root of sum of squares of these 3. So now we can imagine that our molecule is moving towards the wall BCFG with momentum mu1. Since in our assumption we are assuming that all collisions are elastic, it means in any collision there is no loss of kinetic energy. And what is kinetic energy? Half mu1 square. It means if before collision magnitude of velocity was u1, after collision it should be u1. So what will happen? Molecule is moving towards the wall. Which wall? That is BCFG. Molecule was moving towards wall BCFG. It is BCGF with momentum mu1. If there is no loss of energy, it will rebound with the same velocity. Now it will start travel towards the wall. After collision, it will move towards the wall A, D, H, E, and to collide with this wall it has to travel a distance L. So if momentum was before collision mu1, after collision it should be minus mu1. So it means change in momentum in one collision is equals to mu1 minus mu1. So you can understand it should be 2 mu1, not taking direction, only pressure is this. So 2 mu1, in each collision there is a change in momentum of this molecule alone is 2 mu1. How many collisions are there in 1 second? To again collide with same wall, it has to travel 2L distance from BCGF to ADEH. It will travel L distance. After collision it will come back. Again it will travel L distance. So with same wall, it will collide after traveling a distance of 2L. Since its velocity is u1, so time taken by a molecule for next collision I am taking T1 is equals to velocity is distance upon time. So time should be distance upon velocity. It means in each 2L upon u1 second, in 2L upon u1 second, change in momentum is (2m u1). Therefore, in 1 second, change in momentum, it should be 2mu1 divided by 2L by u1. So we are getting mu1 square by L, that is force exerted by this molecule on wall is equals to mu1 square by L. Since area of wall is L square, each face of a cube is a square, so we can calculate pressure. Therefore, pressure exerted by this molecule on wall is equals to, divide this by area, area is L square and L cube is volume, so we can say it should be mu1 square by V. Since all molecule has same mass, they are moving in same container, so M and V is same for all. What is different for second molecule? Its velocity is u2. For third, it is u3. If we add the pressure of all molecules, we will get total pressure of gas in x-axis direction. So therefore, total pressure of gas in the direction of x-axis which we denoted by Px, it should be m by v is common. Suppose n particles are there. What we are assuming? There are total n molecules. Let there are n molecules. So u1 square, u2 square up to un square. Similarly, we can see m and v are common. In which direction molecule will move? If we are considering velocity along y-axis, only there is a change in u. In place of u, we have to take v, so we can calculate now. Similarly, pressure of gas in the direction of y-axis means py, it should be m by v, v1 square, v2 square plus vn square. Similarly, pressure of gas in the direction of z-axis pz, it should be m by v, w1 square, w2 square, wn square. So now we are able to calculate pressure of gas. Px, Py, Pz all are pressure of gas, means all are P. If we add all three and divide it by 3, we will get P, because it is P, it is P, it is P. So 3P by 3 means it should be P. M by V, take them common, what you are going to get? See, from first bracket u1 square, from second bracket u2 square, v1 square, from third bracket w1 square. We are adding first term. What we will get? c1 square, c2 square up to cn square. Now I am dividing this term by n and multiplying this expression by n. So what is m into n? Mass of one molecule into total number of molecule. And I am removing this whole term with one term, c bar square. C bar square. So what is your c bar? C bar square is the mean of squares of velocities. So c bar should be square root of mean of square of velocities. So we are saying c bar means RMS speed. What is your c bar? It is known as RMS speed. Root mean square speed. A very important RMS speed. So this formula, what we got is very important formula. All results you can make from this if you know this. Each numerical, each problem you can attempt. What we assume, m means mass of one molecule. What was n? Total number of molecules. What is c bar? RMS value of molecule. What is V? Total volume of gas. What is P? Total pressure of gas. So now we can make so many results from this. We can make now so many results from this. And that important results we will write here. In this space, we will write that important result which we will deduce from these. See, m is mass of one molecule, n is number of molecule. It means mn should be total mass of gas. So one important result is P is mc bar square by V. Take V on that side. So it is PV. We divided by 3. This 3 should be there. It is 3. It should be there. It was 3. It was 3. We write here. MnC bar. So 1 3 is there, it is that 3 is there, this is that 3. It is that 3, this 3 is there, 3. So now we will discuss one by one what result we can get. Take this 3 on this side. So we are getting mc bar square. Divide both sides by 2. So we are getting this. First, this result was important. Now what is half mc bar square? Half m into velocity square is kinetic energy. Whose mass is m? M is the mass of whole gas. So kinetic energy for total gas, for total kinetic energy for gas is 3 upon 2 PV. So this is again one important result. The total kinetic energy is equals to 3 by 2 PV. They can ask kinetic energy of gas per unit volume, what it should be. In place of volume put 1. It means what you need to answer the kinetic energy per unit volume, only pressure. So they can ask, tell us the kinetic energy of gas at this pressure per unit volume at this pressure. So take 3 by 2 of P, you will get that. One more important result, PV we can put mu RT. So again I am moving from here. So PV is equals to, it is one important result, second number important result, it is third number important result, fourth one, PV is equals to Mn C bar square by 3. But what is PV? PV is mu RT. Take 3 on that side. What it is now? It is now Mn C bar square. If we are taking 1 mole of gas, I am shifting here, then 3 RT. In 1 mole gas, number of molecule is fixed, and that number is known as Avogadro number. So I am getting 3 RT is equals to Mn C bar square. Since it is universal gas constant, it is Avogadro number, both have a fixed value. So we can write, take this N in denominator of L, R, you will get R by N, one new constant, M C bar square. What is the name of this new constant? K. And this T is at its place, T. So we are writing 3 kT is equals to MC bar square. Divide both sides by 2. What we are going to get? Again one important result. 3 by 2 kT is equals to half M C bar square. A fourth important result. So what is it? M is the mass of one molecule. It means kinetic energy of one molecule is 3 by 2 kT. Kinetic energy of whole gas by 3 by 2 PV. But for one molecule, kinetic energy is 3 by 2 kT. Since we considered only the translatory motion of particle, which was possible in 3 directions, 3 dimensions, x-axis, y-axis, z-axis. These are known as degree of freedoms. So this total kinetic energy is associated with 3 degree of freedom. So kinetic energy associated with each degree of freedom, it should be half kT. So one important result again, कि kinetic energy associated with each degree of freedom, with each degree of freedom, it should be half kT. Since diatomic molecules have 5 degree of freedom, so for diatomic molecules, total kinetic energy is equals to 5 upon 2 kT because they have 5 degree of freedom. and for triatomic or polyatomic they have 6 degree of freedom. Polyatomic, so 6 by 2 means 3 kT, that has 3 kT. So getting my point? So in this way we got very important results. You can also make some results for C bar also. What is C bar? M into N means mass, total mass. So we can write C bar is equals to root 3. If I am taking mu 1, for 1 mole mass means molecular weight. So what we will get? 3 RT upon Mn means molecular mass. I am writing mm. So you can get the root mean square speed of molecule by the formula root 3 RT upon mm, molecular mass of the particle. So these were very, very important results. So now some remaining results which are also important we will discuss. See, one Mayer's formula is there. You know that gases has 2 types of specific heat. Specific heat at constant pressure, specific heat at constant volume. If you are taking mass 1 mole, it is known as molar specific heat. Specific heat, you know that heat energy required to increase the temperature of unit mass by 1 degree is known as specific heat. If mass is 1 mole, it will known as molar specific heat. So if gas is at constant pressure, it means volume may be changed, gas can expand. So for expansion, gas need extra energy. If gas is at constant volume, it need energy only to raise its temperature. Because volume is constant, gas will not do any work, because work is pressure into change in volume. That's why Cp is always greater than Cv for all gases. Mayer established one result, a very easy derivation is there. Cp minus Cv is equals to, in joule it is R, in calories it is R upon J. In calories it is R upon J, because heat energy has 2 types of unit. Joule, all energies in SI unit is joule, but generally we are taking unit of heat energy calorie. So there is a relation. If you divide by J, you will get in calories. So it is Mayer's formula, Cp minus Cv. And we know that what is Cv? What is Cv? Just we discussed that the kinetic energy, the energy of the whole gas, if we are talking about, we discussed so many formulas. If we are talking about whole gas, M into N means whole gas, 3 by 2, we can write 8. If mu we are not taking, it is the, if we are taking 1 mole, it is molecular mass, so we will get 3 by 2 RT is equals to kinetic energy of 1 mole gas. Mu, we are taking 1 mole, so it is mass of 1 mole, half m C bar square. So energy of 1 mole gas is 3 by 2 RT. Energy of 1 mole gas is 3 by 2 RT. for 1 mole gas. It was energy. So du by dt, so energy required to increase the temperature. In that we put volume constant, so it should be Cv. What you will get? 3 by 2 R. In that derivation volume was constant. So what we are getting? Cv. So Cv we got 3 by 2 R. And what is Cp? Cp is R plus Cv. So Cp should be 5 by 2 R. We are talking about monoatomic. What about diatomic? Energy should be 5 by 2 R. So for diatomic, Cv means du by dt means 5 by 2 R. So Cp add 1 R, so you will get 7 by 2 R. For polyatomic, U is equals to 6 by 2 means 3 RT. So Cv du by dt is 3 R. So Cp should be 4 R. So remember these important results and the relation between Cp upon Cv with degree of freedom. Cp upon Cv, the ratio to molar specific heat of a gas is known as gamma. Gamma is equals to Cp upon Cv, and it is associated with degree of freedom by this formula 1 plus 2 by n. N or F, by what you are representing, it is degree of freedom. It is degree of freedom. So now for monoatomic gas, degree of freedom is 3, so gamma should be 1 plus 2 by 3. It means 5 by 3, or you can say 1.67. For diatomic, degree of freedom is 5. So 7 by 5, 1.4. For polyatomic, gamma is equals to 1 by 3 means 4 by 3, 1.33. So these were some very important results. And one more thing they can ask, generally they are asking, what we calculated root mean square speed. What was it? Root 3 RT upon mm. So CRMS, root mean square was speed 3 RT by molecular mass. Two more speeds are there. One is known as average speed, C average. It is 8 RT upon pi m. 8 RT upon, only you have to learn formula, derivation is not in your syllabus. And one is most probable speed, most probable speed, most probable speed. All three are in terms of R and M. It is 2RT by M. So if they are asking, sometimes they are asking ratio, so you should learn this. Most probable speed root 2RT upon mm. Means in competitive exams, sometimes they can give this. What is the ratio? CRMS, C average, C most probable speed. So what is common? Remove that. RT by M is common. So remaining is root 3 is 2. Root 8 by pi is to root 2. So it is root 3. It is root pi means 3.14. So 2 point something and it is 2. Means RMS speed is greater than average speed and average speed is greater than most probable speed. So least one is most probable speed and greatest is RMS speed. So now any type of problem they can mix. Keep in mind what is CP and CV. Okay, they can make tough problems on this topic. You know what is gamma? Gamma is CP upon CV. They can put two gases in one container and they can ask, now calculate gamma for this mixture. Then you have to calculate CP and CV for mixture. Then only you can get ratio. How to get CP for mixture? Suppose in your container 2 mole of diatomic gas and 1 mole of monoatomic gas. Individually you know each and everything. If you want to increase 1 unit temperature for 1 mole of gas at constant volume, for monoatomic gas it is 3 upon 2R. For diatomic gas it is 5 upon 2R. So first calculate total amount of heat required to increase the temperature by 1 unit. Getting my point? Then calculate it for 1 mole. Then you will get CP and CV. We will do problems. We will get problems in that. Now we are going to solve crash course problems. So in that we will get this type of problems. We will solve there. But keep in mind this very important derivation and results of this derivations. So now we will solve the problems related to these concepts in our problem session of 45 problems. Thank you.